everyone. Today we're going to be touching on the difference between a pure substance and a mixture, but mostly we're going to be learning how we can apply the mole concept to understand the composition of a pure substance. Before we can do that, we need to figure out what a pure substance is. A pure substance is one that is made up of only one type of thing. So by thing, I mean it could be one type of particle, like one type of atom or one type of molecule, or it could be one type of formula unit. And that term is probably new to you. So let's talk about that for a second. A formula unit is the term we use instead of molecule to describe the base building block unit of an ionic compound. We don't use the word molecule or particle for that because although in your mind you may imagine an ionic compound like, for example, sodium chloride as two particles hanging out or like a few particles just hanging out together, for example, one sodium and one chloride ion brought together by their mutual attraction. That is not what actually happens in real life. In real life, what they're going to do is array themselves in these huge crystalline structures. And it just doesn't make sense to say particle when there really isn't a discrete particle. It's like this huge thing. So instead, we use the term formula unit. Let's look at some examples of pure substances. So you can see the one that everybody's probably thinking of is the single type of atom. In other words, an element. And you see some listed there. Note that some elements will hang out together in pairs just by their nature. We call those diatomic. Oxygen is one of those. So even though there are two oxygens hanging out together, this is still an element. And then, of course, this is still a pure substance. But pure substances are not only single elements. It can be a compound. So I've listed some compounds there: water, glucose, ammonia. Those are also pure substances if there is just one of those in the substance. For example, if it's just pure water and nothing else, that's a pure substance. If it's just glucose and nothing else, that is a pure substance, even though each particle is made up of different elements. That's totally fine. It's just one type of particle. And then I mentioned single type of formula unit, and I mentioned that already. Here's a visual that might help you to sort of organize those ideas. I just want you to pay attention to the bottom left here. Here's just a picture that represents the idea of the formula unit. And that crystalline structure is not even as big as it would be in real life. But you can see we are just focusing on the single repeat as the base unit for that kind of concept. Contrast that with mixtures, which of course must then have more than one type of stuff. I put this little data table here just so you can kind of look back and forth. Reminder, I purposely put insulin in there because it's crazy. Proteins are huge. So it can be crazy like that, but if it's just insulin, it's still a pure substance. And here's just some examples of some mixtures. You can see solutions. You could see this alloy, which is kind of like a solid solution of two different metals. It could be gaseous. It could be heterogeneous, more on that sometime later, like cereal and milk, where you can just, it's not evenly mixed, but that would be a different type of mixture, and coffee. We're going to get back to the idea of mixtures in a later unit and learn some laboratory techniques by which we can separate the component parts of a mixture. But for now, we're just going to understand the idea of it in contrast to pure substances, which is what we're going to be focusing on for the rest of the lecture. The rest of our time in this lecture is going to be spent understanding how we can quantify the composition of a pure substance. In other words, to understand how it is built, using a little math to figure out how it's put together, which of course is going to help us understand what it does. The idea of structure leading to function is not something you can leave behind in biology, unfortunately. It is just the rule of the universe. I listed some reasons of why we would want to do that, but it's just a fundamental piece of understanding what the substance is and what it does and how we could maybe use it or what it's doing to us, etc. So this is, it's pretty simple on the face of it, but it's really, really important. The first way we'll do this is percent composition by mass. Percent composition by mass, aka mass percent, describes how much of a compound's total mass comes from each of its component elements. You'll have some problems, and the first ones we're going to try are where you're just calculating forward like that. You're given the formula and the total mass, and you need to figure out the mass percent. You also may be asked to go the other direction. If you're given the mass percent and the total mass of the compound, you might need to calculate the mass of a specific element. So either direction. Both of these are predicated on the formula that's in front of you. It's not on the formula sheet, so I put a note there, so you do need to memorize it. But if you notice, it's really just a percentage. It's the same way you take the percent of anything. So I think the key here is just remembering that that's what it is. It's not complicated math. It's just if you are looking for a formula for this on the sheet, you're not going to find it. So just notice and remember that you just need to be able to take a percentage for this one. So how do we do it? You will need your periodic table, and if you're doing a straightforward calculate the percent composition type of problem, you will be given the formula. You're going to use the molar mass from the periodic table and the formula to determine both the total molar mass of the compound, which is the mass of the whole, right? It's going in the denominator, and then the total masses of each separate element in the compound. And I put this little note here. You have to account for the subscripts. Remember, they tell you how many atoms are in each of the molecules, but it also tells you how many moles of that element are in a mole of the compound. For example, for water, if you're figuring out the total mass of hydrogen, you need to take the molar mass from the periodic table and multiply by 2, because every mole of water has 2 moles of hydrogen, right? Let's do an example here to show you what I mean. For this one, we're going to calculate the percent composition for lithium hydroxide. Notice here that each of the component elements has a subscript of 1. There's no number there, and the secret subscript is 1 if there's no number. So you can just take it straight from the periodic table, and you can see that I've put that in the numerator for each of these. And then the denominator is the total molar mass of the compound, which you get by adding up all of the components, right? After you have simplified and multiplied by 100, you get the percentage each of lithium, oxygen, and hydrogen. So the math is pretty straightforward. It's just a percentage. You just have to remember that that's what you have to do. All right, now you're going to try one. I want you to calculate the percent composition for copper 2 chloride, and I've given you the formula there. We are going to learn how to figure out the formulas from the names later. Pause here and try this one. And I put a little note for you. Pay attention to the subscripts. All right, did you get it? Here is the answer. Please check your work and see if you got the right answer. If you did not get it and you don't understand what went wrong, put a note and we'll talk about it in class. Going the other direction is even simpler. For this, you just have to multiply the percent in decimal form. So for example, 45% becomes 0.45 by the total mass of the compound to find the mass of a particular element. So for example, if we're trying to find the mass of each element in a 68.2 gram sample of lithium hydroxide, using the percent, I didn't relist them, but we're using the percentages that we just calculated. You can see what we do here. We just have to take that mass, 68.2, and multiply by each of the separate percentages in decimal form to get the mass of each component part. All right, now you try one. Let's take the copper 2 chloride that we just did. You use the mass percents that you just calculated and find the mass of copper in a 452 gram sample of copper 2 chloride. Pause here. And there you go. Did you get it? I knew it. You're so smart. Now we're going to consider how to evaluate irregularities in problems like this. You will sometimes have straight up mass percent questions, but for whatever reason, College Board will often frame the questions on this skill around a lab irregularity. So for example, you'll have some kind of experiment described and something will have gone wrong along the way. So they'll have some kind of equipment failure, or there was a spill, or the reaction didn't totally proceed, or the student did not drive off all of the water from their sample that was supposed to be weighed dry, etc. For these, really, the irregularity part is just a logic question. You just kind of have to, I mean, I don't know. There's no like formula for this, but they're pretty straightforward. If you think about what's going on, it's not that hard, I don't think, to figure out how that would affect your mass. And after that, it's pretty simple, little hop, skip, and a jump over how that would affect their calculations, as long as you understand mass percent in general. So for example, this first one, if they're meant to be weighing their sample dry, like all the water is supposed to be driven off and they didn't complete that process, that would add mass to their solid sample, right? Because there's extra water. If they spill or lose product in some other way, that's gonna artificially reduce their mass. It's that stuff. That's what the logic piece. And then you just have to, use your skill of mass percent to answer the rest of the question. So let's try one of these. The question is, the mass percent of carbon in pure methane is 75%. A chemist analyzes an impure sample of methane and determines that the mass percent is significantly less. Which of the following impurities could account for the low mass percent of carbon in the sample? So it's multiple choice. Here are your options. Which one of these, when added to their sample by mistake, would artificially reduce the mass percent calculated for carbon? Take a moment. And the answer is water, because that's the only one that would not artificially inflate the percentage. Water, of course, contains no carbon. So if water is included in that mass that we thought was all carbon, then the calculated percentage of carbon that we would find would be lower. The other three have a higher mass percent than 75. So if those were added in, the direction of the arrow would be the other way. It would be artificially inflated. Let's try another one. A 25-gram sample of aluminum bromide may contain measurable amounts of other compounds as impurities. Which of the following do you need to determine that the sample is pure? So read through those answer choices. Take a moment, pause. All right, and the answer is A. This is an example of one where they framed it as an impurities question, but it's really not. It's really just, do you know the procedure? Because it's asking you, what do you need for that? Just general procedure. Next topic is empirical and molecular formulas. One of the things we can do with percent composition, if we have the molar mass, is to figure out the substance's empirical and molecular formulas, which are just another way of quantitatively understanding the substance's structure. So what are these? Jump down to the green molecular formula, because this is going to be the one that's more familiar to you. By the way, this actual particular formula is maybe familiar to you. Does anybody recognize that one? If you said glucose, then I'm so proud of you. Yes, the time in the metabolism unit in biology was well spent. Anyway, this is the formula that describes the actual structure of the molecule, like the actual ingredients. If you look at the little picture I put, this is glucose in its ringed form, and you can see that the subscripts in the formula do match the actual structure of the molecule here. All the blacks are carbons, the reds are oxygens, and the silvers are hydrogens, and if you count, it does in fact match. This is reality. The empirical formula is the simplest ratio of one element to another, and that may or may not match the reality. It may or may not be the same as the molecular formula. It's more commonly the same for really small molecules. For example, H2O, water. For that one, you can't get simpler than 2 to 1 and stay with whole numbers, right? If you divided by something, it would get a decimal, and we don't do that. You can't have like part of an atom. So in that case, the empirical formula and the molecular formula are the same. It is more common for them to be the same for smaller molecules than for the really, really big ones, because that's just like how numbers work. But you should be aware that it could be the same and it could be different. So I think it's pretty obvious why you would want to know the molecular formula, like the real formula. And you may be wondering, like, what is the point of the empirical formula? It can be helpful to just see a simpler version of those ratios, especially for the like big gigantic hydrocarbons like proteins, whatever. You can imagine why it would be nice to have a simplified version of the ratio. But more commonly, the empirical formula is the easier one to figure out from your lab data. And you can use the empirical formula to get to your true goal, which is the molecular formula. The word empirical means like from data or like from the lab, and it really just means the one that you figured out from your lab data, and we would use that to make the molecular formula. So let's learn how we would do this. This one, I just feel like we need to just walk through an example to see how to do it. So here's our example. We have a compound that's found to contain 56.5% carbon, 7.11% hydrogen, and 36.4% phosphorus. And we're going to use that mass percent to determine the empirical formula for the compound. So the first thing we need to do if we're given percentages for this kind of a problem is to turn them into masses. We need masses. And the easiest way to do this with nice, happy numbers is to assume a total mass of 100. And that way you can just switch the units and now you have masses. As you can see, I've done here. Next, we have to convert those masses into moles. This is the step that students forget. So if you're going to make a mistake in this process, it's probably going to be this one. And I want you to understand why we have to do this, because I think that's going to help you to remember to do it. We cannot use the grams directly because remember, ultimately, we're trying to count how many of each type of atom are in the molecule. And we cannot count directly with masses because each element has a different composition and therefore a different atomic mass, a different molar mass. And so those masses for each of them represent different numbers of particles. So we have to get to moles first, and in that way we can go directly from that to a count. So you can see that I've done a molar conversion for each. This is just your regular or schmegular molar conversion. Once you have moles, you are almost home free. Now we're just going to divide each of those mole values by the smallest one to get us to ratios. So you can see the smallest one in this case is phosphorus. So I've divided that by its number of moles, its number of moles by its number of moles. And then each of those for carbon and hydrogen, I've done the same. When you get these numbers, you're going to analyze them. Are they very, very close to whole numbers, meaning within 0.1? In this case, they are. If they are, then you can round to whole numbers because what you're looking at is just experimental error, right? Or just calculation error. And so we are at whole numbers. And in that case, you are done. If you get there and you are not very, very close to whole numbers, for example, you have a 2.5, that is not close enough. Instead, you need to multiply all of the subscripts by the smallest value that you need to give whole numbers. I put a little visual guide on your note sheet. You don't need to like memorize that or anything. I mean, you can just kind of figure, this is one of those things you just kind of figure it out by guess and check if nothing else. But I just thought it might be kind of a good visual to give you an idea of what I mean, what those numbers that you multiply by might be. It's usually like 2 or 3. We didn't have to do that in this case because we were already at whole numbers. So you just pop those in as subscripts, remembering that if you have a 1 that you don't actually put it. The secret subscript, if there's no number, is 1. And if you put the 1, it just makes it look like you don't know what you're doing. So don't put the 1. All right, so we're at the empirical formula. Is this the actual formula? Is this the molecular formula? Like I said before, maybe, maybe not. So we need to do a little bit more analysis to determine that. Before we get into that, though, I want you to try one of these. So pause here and see if you can answer this question. All right, the first thing we need to do, of course, is to convert those percentages into masses. I didn't show that calculation because I just don't think you need me to show you again. But here I have the grams, and I did a molar conversion to turn those grams into moles. And then for each, I divided by the smallest. In this case, it was the phosphorus. And when you look at my answers, I then multiplied by 2. Why did I do that? Well, if you look at the zinc, it's 1.5, which is not close enough to assume that it's a rounding error. So I needed to multiply by the smallest amount that would give me whole numbers, and that was 2 in this case. So then I end up with 3 and 2, and there I have my empirical formula. There's one other way you may be asked to do that, and that's by something called combustion analysis, which is analyzing the products of a combustion reaction and working backwards to figure out the empirical formula. Don't be afraid. You don't have to understand the reaction yet. We're doing that later, okay? You just have to notice what's in there. The pattern is always the same for a combustion reaction. You have some kind of hydrocarbon, typically. I mean, there are exceptions, but it's almost always a hydrocarbon. Sometimes it's just carbon and hydrogen. Sometimes it's something else. That something else is usually oxygen. It's burned in oxygen, so you can see the oxygen gas here, and that's going to produce carbon dioxide and water. You may feel like this is sort of familiar. This is the cellular respiration reaction, which that is actually a stepwise combustion reaction. And that's what we're looking at. So we're going to be really looking at this carbon dioxide and water in the product side, and then working backwards to figure out what was going on with that hydrocarbon. That would be like our mystery, even though we see it here. So how do we do this? First, you're going to convert the given masses of carbon dioxide and water into moles. They will give you those masses, or sometimes they'll give you the moles even. Then you're going to convert the moles into moles of carbon and hydrogen. How do you do this? Well, look at the formulas, look at the subscripts. For every mole of carbon dioxide, there is 1 mole of carbon, right? The subscript next to carbon is 1. There's nothing there. That means it's 1. And there are 2 moles of hydrogen for every mole of water. And I know that because the subscript next to the H is 2, and that's telling me there are 2 moles of water for every mole of, 2 moles of hydrogen for every mole of water. So for that, you're just basically multiplying the moles of water by 2. That's how you do that part. Okay. Then you have to look and see what information you have about the original compound. If the original compound has another element in it other than carbon and hydrogen, like I said, that's often oxygen, sometimes something else, then you have to find the mass of that. And you're going to do that by turning the moles of carbon and hydrogen into grams, into masses with a conversion, and subtracting that mass from the original mass of the compound. If that sounds like what, don't worry. We're going to do an example and you'll see what I mean. It's simple. Once you have that mass for that other element, like for example, oxygen, you turn that mass into moles, and then you have moles of everybody, and then you just go on like you would with the other just regular problems. All right, let's try one of these. It's asking for the empirical formula of isopropyl alcohol, and it's telling you it only has carbon, hydrogen, and oxygen. And then it's giving you a total starting grams. So you have the mass of the isopropyl alcohol, and it's telling you how much carbon dioxide and water are produced in mass as well. So the first thing we have to do, like we said, is convert the grams of carbon dioxide and water into moles of carbon dioxide and water, and then to moles of carbon and hydrogen. So this is just a molar conversion first. So we went from grams of our products into moles of our products. And then we know that for every, and I showed this as like a full-on math thing, but you really are just multiplying the water by 2, because we know that every mole of carbon dioxide has a mole of carbon, every mole of water has 2 moles of hydrogen. So now we have mole numbers for carbon and hydrogen. If it was just a hydrocarbon that didn't have anything else, we would be good to go on to the next step. But we were told that it contains oxygen. So now we need to do some extra stuff to figure out how much oxygen was in the original molecule. So for this, we're going to take the moles of carbon and hydrogen, convert those into mass, and then subtract the total of that mass from the original mass of the entire compound. So let me just show you. Okay, so we have the moles of carbon and hydrogen. This was from our last step. We're going to convert that into grams, doing just a regular molar conversion. And then we know the problem tells us the original total volume was 0.255 grams. And we know that we have grams, or the mass of the carbon and hydrogen. So if we subtract that from the total, whatever's left over has to be our oxygen, right? So now we have the grams of oxygen, and we convert that into moles. So now we have molar values for all 3. Now we're back in familiar territory, thank goodness. And we can just do what we did before. We're going to find the smallest one and divide by that to find ratios. You'll notice that in this case, we are within 0.1 of each. We're pretty close, so we can consider those rounding errors. And then we have our whole number subscripts. Once you have the empirical formula, if you're given the molar mass, you can figure out the compound's molecular formula. So let's try that with the molecule we were just working with. They're telling us that the molar mass is 170.14 grams per mole and asking you to find its molecular formula. First step is to find the molar mass of the empirical formula, and you're going to do this by multiplying the subscripts by the molar mass of each of the component parts and adding it up. Then you're going to compare the number you just got for the empirical formula to the known molar mass. If they are the same, then the empirical formula and the molecular formula are the same. Hooray. If they are not the same, then you just need to do a ratio like you did before to figure out the multiple that will get you to the molecular formula. So let's look at that. We just put the larger one over the smaller one, and when you divide, you get 2. That just means that you need to multiply all of the subscripts by 2 to find the molecular formula. So for us, this C4H6P becomes C8H12P2. Easy peasy. All right, I want you to do the whole thing start to finish. You're given the mass percent, you're given the compound's molar mass, you are to find the empirical formula first and then the molecular formula. So pause this and try it. All right, so let's go through all of this. So first, finding the empirical formula. We had to convert the percentages to masses. I just did that off screen. And then those masses to moles. And then we do our ratio. We come up with 1 and 2.5. We know we can't let that stand. So in order to get whole numbers, we need to multiply it by 2, and that gives us an empirical formula of P2O5. Then we're going to compare our known molar mass to the molar mass of the empirical formula that we just found. And I just put the little math here. Our empirical formula, when we add everything up, comes to 141.94 grams per mole. And we can see that those are not the same. So in order to and when comparing, it's double. So we need to multiply our subscripts by 2 to give us P4O10. Did you get it? Very good. And just for funsies before you go, let's do an exam question. This is question 2A from the 2025 FRQ about this topic we were just learning. So pause here. There is a little bit of figuring out to do. You know how College Board likes to do. So a little bit of figuring out. Let's see if you can do it. So pause. All right, and here are the answers. The first part's really straightforward. You can see that it's just a molar conversion. So they give you the mass of water, and they're asking you to turn that into moles. And then the second part is the part where there might be a little bit of figuring out. So first they want you to convert the moles of water into moles of hydrogen, like we have done by multiplying by 2. And then they're telling you up here that the moles of carbon dioxide are 0.24. And that means that the moles of carbon are also 0.24, because remember, there's 1 mole of carbon for every mole of carbon dioxide. And so if you're given that, and you're given you've already calculated the moles of hydrogen, and they're telling you that it's a 1-to-1 ratio of carbon to oxygen, you know that the oxygen is also 0.24. Then you can do it. They're showing you a couple of different ways. Like the ones that are printed on the page are like just kind of vibe it out, kind of like ratio. But you can solve it the way we did. Once you have these moles, you can solve the way we did before by dividing the biggest by the smallest and then multiplying if needed, which you would need to do in this case, and you would end up with the correct empirical formula. All right, that one was kind of a hard one. Great job, you guys. I will see you tomorrow.